Hi everyone, this is Yuan-Hao from Academia Sinica Taiwan. Today I'm going to talk about the random forest techniques for systems with non-volatile memories. First, I will have some introduction to random forest and non-volatile memories, and then I will talk about some random forest techniques for systems with non-volatile memories, and finally I will give a conclusion. In the big data era, the data volume is skyrocketing and data are loaded into main memory for better efficiency, but in this way, big memory is needed to process big data. Due to the lower unit cost, non-volatile memory has the great potential to meet the demand for big memory, and in this figure, we can find that more and more data are placed in non-volatile memory. The rate of data generation surpasses the growth of memory capacity, so NVM is not big enough in practice. It is impractical to load all the data into NVM in advance, so intensive data movements still exist and are harmful to non-volatile memory. A decision tree is to predict the target result by learning simple decision rules inferred from the data features. For example, should we go for a sightseeing to the lake? And we can use the decision tree to consider the weather and then decide whether we want to go to the lake. However, a single decision tree often shows low reliability because of the overfitting problem. A random forest is a collection of weaker decision trees. To avoid the overfitting, each decision tree is randomly generated by a subset of training data, and altogether they can build an ensemble of decision makers by voting for the result. And there are several advantages. First, it has very high prediction accuracy, high efficiency over the large dataset, and a low training cost compared with the neural networks. First, I will talk about the backend strategy for NVM. In the backend phase, we will randomly select data samples to train the decision tree and run for several rounds to form a decision tree forest. And in the ensemble phase, we'll take a majority vote or an average over the results of decision trees. Due to the random selection process of backend, the probability to select any sample data from the dataset is about 63% in a single round of backend. That is about 63% of data in the training dataset will be sampled by each backend round to train the decision tree. In this way, some data may be resampled to form decision trees in any two consecutive rounds of backend, and about 63% of data are resampled from the previous backend round. Therefore, it will introduce a lot of unnecessary data movements. Based on the above observation, we propose an NVM-friendly backend strategy to reuse the active data for a random forest. The main idea is to treat the randomness of the random forest for endurance and performance improvement for NVM memory. And our contribution is to keep the prediction accuracy while achieving good reliability on NVM memory. The main idea of the active data reusing is to pin some data in the main memory for the next runs. For example, the blue ones are pinned in main memory for the next run, but it will cause the wear unleveling issue because the blue ones will endure fewer writes than the green ones. To resolve the wear unleveling issue, we propose a margin-based reusing policy by combining the active data reusing and wear leveling. By properly selecting the reused data with the margin pivot, that is, we will move the margin pivot forward on each round. For example, in the second round, we will reuse the first 4 frames, and in the third round, the pivot is moved forward. Therefore, the next 4 frames are reused to achieve the wear leveling. 3 traces were used for evaluation, and 70% of data were used for training, and 30% of data were used for validation. And the forest size is defined as the total size of random forest to the dataset. The following figures are used to show the right reduction of effectiveness of the proposed strategy, and the x-axis is the forest size. The y-axis is the number of right axes. And we can find that the amount of right reduction is positively related to the reused ratio. In this figure, we find that the reusing ratio has less impact on the error rate, and the error rate drops more significantly when the forest size grows. This means that the forest size is more dominant than the reusing ratio. In summary, the proposed MVM-friendly packing strategy can achieve both the right reduction and well leveling, and by reusing data samples during the packing, the proposed strategy can save the right access with nearly no degradation on the prediction accuracy. Now we shift our focus to the pruning stage of the random forest construction, and we propose the dual-phase pruning to increase the energy efficiency and reduce the write latency. Decision tree is the basement of the random forest algorithm. A tree-based structure consists of the three major components. Internal node is the taste and the attribute. Branch is the outcome of a taste, and the leaf node is the result for a prediction process. On the right-hand side is an example. The internal node is the taste and the attribute age, and it will generate two branches. And on the second level is the taste and the attribute sex, and the outcome has two branches, that is female and the male. And in the leaf node, female is the result. In general, a decision tree is a fully grown decision tree, and it will stop growing when there's only single one class in the node, or there's no attribute for node splitting. But a free ground decision tree usually have the overfitting problem. To avoid or solve this problem, the post-pruning strategy are usually used to cut the redundant nodes off. For example, on the right-hand side figure, the green nodes are cutting off by the post-pruning strategies to avoid the overfitting problem. After the post-pruning, the redundant nodes are cut off. On the other hand, phase change memory is the very famous non-volatile memory. It has some nice features such as the high cell density, non-volatility, and faster read performance. But it also has some drawbacks such as the expensive writing cost. Therefore, the multi-level cell PCM supports multi-write mode. The high-cost writing mode, it takes longer write latency and higher energy consumption, but it can retain data for a long time. And the other is the low-cost writing mode, but it can only retain data for a shorter time. On the other hand side, there's a figure to illustrate the retention time of the two modes. The upper figures shows the high-cost writing mode because the blank space between each state is wider. Therefore, the data can be retained for a longer time. The bottom figure, each state has a narrower blank space. Therefore, the retention time is shorter. Based on our observations, we find that the redundant nodes will be pruned by the post-pruning strategy, and the nodes will become the unnecessary writes to the non-volatile memory because during the training process, data written to non-volatile memory are persistent. Therefore, our goal is to reduce the writing cost, including the energy consumption and the latency resulting from the unnecessary writes. Therefore, by utilizing the multi-write mode of the PCM, we are trying to hybrid the low-cost writing mode and the high-cost writing mode. That is to use the low-cost writing mode for the unnecessary writes and the high-cost writing mode for the persistent decision tree nodes. But how to have an accurate prediction is the quick question. To answer this question, we propose the dual-phase pruning framework that combines the pre-pruning and the post-pruning strategies. The dual-phase pruning framework is composed of three major components. The first one is the pre-pruning checker. This checker is to identify the to be pruned nodes in the decision tree and mark these to be pruned nodes as the high light right nodes because they are going to be pruned. Therefore, we don't need to spend too much energy to maintain those data. And the second component is the node tracker. It is to track the head of the light right subtrees. Therefore, we will know which is the starting node for the pruning. And the third component is the planer. That is to rewrite the light right nodes in the normal writing mode. If the light right node is not pruned in the post-pruning phase. The main goal of the pre-pruning phase is to conserve the energy consumption for writing the unnecessary nodes. But how to identify the unnecessary nodes? We include the two parts. The first part is to combine the pre-pruning strategy, such as the chi-square test and early stopping. The second one is to identify which node should be written in the low-cost writing mode. For example, the secondary checker can be used as the test to see whether this node will be possibly pruned in the post-pruning phase. Therefore, we can use the light write mode to write it. The main goal of the node tracker is to keep the information of light write nodes for checking those nodes in the post-pruning phase. And the node tracker includes the tracking list to point to the head of the light write subtrees. For example, on the right-hand side figure, F32 is the root node, and F16, F20, F33, and F18 are the head of the light write subtrees, and they are possibly will be pruned in the post-pruning phase. Therefore, they are written with the light write mode. The main goal of the post-pruning phase is to maintain the prediction accuracy in the proposed framework. However, during the post-prune decision tree, some tree nodes in the tracker will not be pruned. For example, on the right-hand side figure, there's one node that is not pruned. Therefore, we need to rewrite it with the high-cost write mode because if we do not rewrite it, the data will be lost. And for the other nodes that in the tracker, that will be pruned, and we will just skip it and ignore it. The proposed framework was integrated into the famous Ranger, and we collect the amount of read-write traffic to memory and simulated the energy consumption and I/O performance on the ambient device. And the evaluated metrics are the energy consumption and the latency. And when the proposed framework was compared with the pre-pruned tree, a post-pruned tree, and the foreground tree. As shown in this table, we can find that the dual pruning achieves the highest prediction accuracy, which is the same as the post-pruning. However, the pre-pruning has a very low accuracy, which is unacceptable for most traces. As for the energy consumption, compared to the post-pruning strategy, the proposed dual-phase pruning can reduce a lot of energy. For example, you only consume 87% of the energy under the digit minutes trace, and only consume 69% of energy under the credit card trace, and only 69% of energy under the facial minutes trace. Therefore, it can reduce the energy consumption up to 30%. As for the latency, the proposed dual-phase pruning can reduce the latency for tree construction by up to 16.7%. In summary, the proposed dual-phase pruning framework can reduce the energy consumption of the decision tree construction. because it can correctly track in the unnecessary nodes and write them in the low-cost writing mode. Therefore, it can save the energy consumption for up to 30%. In conclusion, in this talk, we demonstrate some approaches to tackle the random forest issues over ambient-based systems. By using the data samples during bagging, we proposed an ambient-friendly bagging strategy to save the write access with nearly no degradation on the accuracy. And by utilizing the multi-write modes and the pruning feature of random forest, a dual-phase pruning framework was proposed to reduce the energy consumption of the tree construction over MLC PCM. Thank you.